In this general sensors, first we are going to focus on touch and pain. Then we will move on to special sensors. General sensors, touch and pain. First and foremost, to feel touch, to feel pain, you need receptors. The touch receptors. Very, very high yield. Definitely one question sure shot these days. Now look into this picture, my dear friend. How many touch receptors are there? 4. Out of this 4, first is superficial, second is superficial, the third one is deep, the fourth one is also deep. What are the name given to them? Superficial, Meissner. Superficial, Merkel cells. Pacinian corpuscle is deep, Ruffiniatics are deep. Most important table, definitely MCQ is going to come, so listen very carefully. Why you need Meissner corpuscle? Discriminatory touch. You call that 2-point discrimination, right? It is possible because of Meissner corpuscle. Second important point, a simple ant crawling in our skin. The gentle strokes is going to make the ant is detected by our Meissner. So Meissner is for discriminatory touch and the stroking. What about Merkel cells, sir? Blind people, very sensitive to edges. What is the system used by blind people? Braille reading. No controversy, no doubt. Always remember, blind people, Braille reading sensitive to edges, Merkel cells. Pacinian is located deep. A deep touch can stimulate them. What is this deep touch? Is a pressure sensation. But most importantly, remember it like you remember our national anthem, Jana Gana Mana. Vibration, most important one is Pacinian corpuscles. Finally, Ruffin is ending sensitive to skin stretch. Now adaptation. The receptors ending with the corpuscles are rapidly adapting. Ending with the corpuscles are rapidly adapting. The remaining 2 are slowly adapting. Excellent. So which are all superficial, which is deep, 2-point discrimination, Meissner.
Pacinian corpuscle, Meissner corpuscle is
Braille reading, Merkel. Pressure, vibration, Pacinian corpuscle. Skin stretch, Ruffiniating. Which is rapidly adapting? Corpuscles are rapidly adapting. The remaining 2 are slowly adapting. Touch receptor. Next is the powerful pain. Pain changes every single human being. To sense pain, you need receptors. Free nerve endings of A delta and C fiber. The receptors are free nerve endings. A very important table is coming. What is this A delta? What is the C fiber? This A delta is responsible for the first pain. You have a pinprick, you have a sharp pain, first pain. So during the night time, the same pain persists. A delta is for the first pain. The same pain that is persisting during the night time
is for C.
Slow pain or second pain, C fibers. So A delta, first pain. C fibers, second pain or slow. So this first pain is fast, the second pain is slow. Remember, this A delta fibers are myelinated, true.
Hello,
C
Nandan
fibers
Gupta,
are
hello.
unmyelinated, very true. What is the pathway that carries them? Relatively new means new spinothalamic tract. A delta. C fibers are very, very old. That is why paleo-spinothalamic tract.
Old.
A delta, first pain, new. C fibers, second pain, paleo. The neurotransmitter for this A delta is glutamate. The neurotransmitter for this C fibers is substance B. Very important. Very, very important, guys. A delta fibers is for fast pain, C fibers are for slow pain. Glutamate for A delta, substance B. B for C fibers. Now, we all know we tend to go to massage because massage is comforting. Massage relieves pain if done properly. What is the reason? Very important theory is behind this gate control theory of pain, which was actually proposed by Melzack and what? See guys, during massaging, we are gently touching a slight amount of pressure we are giving. How it is reducing the pain? Simple. First and foremost, look very carefully. Any non-painful sensation by a gentle touch, by a soft hand, reduces pain. Okay? Non-painful sensations reduce painful sensation. For that, first and foremost, there is a projection neuron in spinal cord. If it is activated, pain will be projected. Projection neuron in spinal cord is going to project pain to the sensory cortex. If you want to feel pain, then pain fibers obviously. A delta and C fibers activate this projection neuron, so pain will be projected to sensory cortex. But what we are doing in massaging, a lateral pathway we are going to activate. This touch, my dear friends, A beta touch or recently transcutaneous electrical nerve stimulation, all these things is going to activate an inhibitory neuron. This inhibitory neuron is going to inhibit our projection neuron. So a touch fiber is activating an inhibitory neuron. That inhibitory neuron will inhibit the projection neuron, so pain will not be projected. This is the side pathway I told you. How are we indirectly inhibiting pain transmission? By inhibiting that projection neuron. Touch fibers activating an inhibitory neuron which inhibit our projection neuron, so pain will not be projected. So what is this theory? Gate control theory. So this TENS also based on this gate control theory. Massaging also gate control theory. Simple. Next. Another very common thing. It is no longer considered to be a quark therapy. People use this needle to relieve pain, acupuncture. What is the physiological basis, sir? We have endogenous opioid analgesic system which is going to get activated. Where it is located, a very important brain area, periaqueductal gray matter. So it is going to release endogenous morphines. What we call them as
Endorphins.
endorphins.
Endogenous
So this important
morphines.
type of
Endorphins.
acupuncture, for
Morphins.
example, is going to activate periaqueductal gray matter, leading to release of endogenous morphines, which are our endorphins that relieve pain in acupuncture. So acupuncture pain relief is because of release of endogenous opioids from periaqueductal gray matter. Now, you see a lot of our friends, this is very fashion these days to lie bare body in a beach to get tanned. See this individual, so much of redness in his skin. So after this relaxation, if he actually go to take bath, what will happen? This reddened area, whenever water touches here, he will simply feel pain. This redness actually induces pain. But normally during taking bath, we don't feel pain. But this area is sensitized. If water touches here, he will feel pain. What is this called as, sir?
Allodynia.
What is the meaning of allodynia? A
Hi,
non-painful
SHK.
stimulus
Hi.
like our day-to-day bathing. If it induces or if you feel pain, that is called as allodynia because this area is sensitized, reddened. So small touch by a simple drop of water is inducing pain. So what is allodynia? A non-painful stimulus is experienced as painful. The recent most NEET MCQ. A non-painful stimulus is experienced as painful. Allodynia. Right. This touch and pain information have to be conveyed further.
Hello.
First they move to spinal cord using dedicated pathways. We call somatosensory pathways. That means exclusively spinal cord tracts. Two important tracts, my dear friends. Dorsal column pathway and anterolateral pathway. This dorsal column pathway is needed for transmission of proprioception.
Dorsal column. This is important. Okay. Dorsal column pathway is for the ipsilateral loss of ipsilateral proprioception, touch and vibration. Dorsal column, same side, ipsilateral proprioception, touch and vibration. Let me give. Let's see.
Transmission of touch sensation is needed for transmission of vibration sensation, dorsal column. On the other hand, anterolateral pathway is very critical for transmitting pain and temperature. From this diagram, tract pathway, we are going to observe one thing. Exclusively in the spinal cord, our dorsal column, remember, our dorsal column is traveling in the same side. That means it is ipsilateral. Exclusively in the spinal cord, our anterolateral pathway, we are clearly seeing with comparison, it crosses to the opposite side. And as
Eight spinal cord
crossing is
cross
called contralateral pathway.
Nebula में joint
Easily
cross
understand.
करो.
Dorsal column in spinal cord remain ipsilateral. Anterolateral pathway in spinal cord cross to the opposite side, contralateral pathway. So dorsal column is ipsilateral, anterolateral pathway is contralateral.
Contralateral.
So you need to remember this. Another recent NEET MCQ, every year they are asking this question.
Brown-Séquard
Any section of
syndrome.
spinal cord. What is this syndrome, sir?
Brown-Séquard syndrome.
One half of spinal cord is destroyed. These individuals will have ipsilateral loss of one, contralateral loss of one.
एक बार
The understanding we had already. So Brown-Séquard syndrome, Same-sided loss of dorsal column senses,
Oh,
for
nice,
example,
nice,
touch
nice.
sensation
Okay.
loss, for example, vibration loss on the same side. The contralateral loss of pain
And
and
temperature.
temperature,
Yes.
very important.
Yes.
So in Brown sequence syndrome, same side loss of dorsal column senses, opposite side loss of anterolateral cortex senses. Brown sequence syndrome, hemisection of spinal cord. Now, from spinal cord, through these pathways, the information goes to the relay center thalamus. Which important nucleus, sir? VPN, which stands for, remember, ventropostrolateral nucleus, exclusively for touching pain. So the thalamic nucleus is ventral postrolateral. From thalamus, eventually going to the final end point, final destination, sensory cortex. So if someone is touching my thumb, on closing my eyes itself, I can say someone is touching my thumb, someone is touching my index finger. How is this possible? Because the sensory cortex knows there is something called thumb. It is represented, what we call this representation.
Weber
We call this
stretches law.
representation as homunculus.
Homunculus.
What is this homunculus? Body parts are represented in sensory cortex. Some parts are magnified, some parts are very minimal. That means the representation is not uniform. Most important first point, the representation is exclusively based on the use of the body part. I keep on using and keep on writing, speaking, writing. The maximal used body parts now are lips and thumb. So we are clearly seeing lip region is having a huge representation. Thumb is having a huge representation. So the representation is based on the use. Most important part. Lips and thumb has got the maximum representation. In our body, trunk and back are very huge. But here, look very carefully. The trunk region, the hip region, the representation is very, very small. That's all. So the representation is based on the use of the body part. I'm sitting, but I'm maximally using what? Lips for speaking, thumb for writing. So maximal representation for lips and thumb, minimum representation for trunk and back in the sensory homunculus. Very important. Based on the sensory homunculus, another recent NEET PG MCQ, what is that, sir? Based on this law, which is called as law of projection. That means, I told you the same example. If you touch my thumb region, the information will always be projected towards the cortex. So I can feel someone is touching my thumb. This is law of projection. By any chance, because of any abnormalities, for example, diabetic foot, if it goes to a situation like that, individual foot have to be amputated. If this foot is amputated, what will happen? The nearby areas like leg region will encroach this foot region. So this foot is no longer there because it is amputated. So the nearby leg region will come and encroach this foot area. What we call this cortical plasticity. So even though this foot is not there, the individual still feels pain because the leg area encroached there. What is that pain called as a phantom limb pain? This phantom limb pain physiological basis is cortical plasticity. What is the meaning of cortical plasticity? If the area is not there, a nearby area will encroach onto that area, whichever that is lost. A nearby area will encroach onto that area, whichever lost. So cortical plasticity is the basis for phantom limb. One more important concept, another recent MCQ. Please show me your hand. In this hand, first I am placing 1 kg weight. Above this 1 kg, if I place a very minute, minuscule 10 gram, where is 1 kg, where is 10 gram? 10 gram is very minimum. Do I feel the increase in weight? Definitely. On the other hand, to the same 1 kg, if I place 100 gram above, definitely I will feel the increase here. That means what? If you just put a very small 10 gram, it is not noticeable. If you put 100 gram, definitely the change in weight is noticeable. That means you have to increase 10 times. It is the logarithmic increase. That simply means magnitude of sensation felt is directly proportional to the log intensity. See, we increased 10 times. So that log increase in intensity is very important to feel the magnitude of sensation. So what is this law called as? Weber-Fechner law. Very important. So law of projection, cortical plasticity for phantom limb. This Weber-Fechner law, it is proportional to the log intensity increase is very important. Into 10 times you have to increase to feel the change in weight. So magnitude of sensation felt is directly proportional to the log intensity of initial stimulus. This is about general senses. Now let's move on to special senses. The first one is obviously the gifted one. What we have is vision. For visual processing, the information first start in the retina, then it will move to thalamus and finally to visual cortex. So where we shift our attention first to the retina. So what is there in retina, sir? Cells. Remember, very, very important concept, guys. Retina cells, there are 7 in number. Look very carefully. The first one is actually shaped like a rod. We call them as rods. The second one, clearly it is looking like a cone. This is our cones. These rods and cones send their information to a cell that is having 2 poles. So having 2
Bipolar
poles,
cells.
what is this? They are our
Rods,
bipolar
cones,
cells.
bipolar
These
cells.
bipolar cells eventually project to the most
Ganglion
important
cell.
cell, fourth cell. What is that, sir? Remember,
Ganglion
cells. So 4 cells we have seen.
Ganglion cell માંથી
Rods, cones,
નીકળે.
bipolar cells, ganglion cells. Now we are going to see 2 connecting cells. What are those 2 connecting cells, sir? The first
Horizontal
one
cell.
is called as horizontal cell. The second connecting cell we are seeing here. This cell, look very carefully. What is the second connecting cell? We call this as amacrine cells.
Amacrine cells.
So 6 cells we have seen.
Hmm.
Rods, cones, bipolar, ganglion, horizontal,
Horizontal,
amacrine. They all have a rolling vision, except only one lost cell, no
Muller
rolling
cell.
vision. It's a simple supporting cell. What we call these cells, remember, they are our Muller's cells. I told you it is the only exceptional cell that is having any rolling vision. So no roll in vision Muller cells. Remaining 6 cells have got a rolling vision. So you'll see the salient features of
Muller
the cells.
cell,
First,
Muller
obviously, is our
don't have
rods.
any role.
We all
Muller,
know it is
Muller
the
don't have
receptor
any
for
role.
dim vision or night vision. Imagine by yourself, if you are clearly seeing in night time means it is more sensitive to light. Even the slightest amount of light it is speaking. So
Road,
rod cells are more sensitive to light, night vision. Cones,
road
very
ઉપર
important for day vision. Most importantly,
રાત્રે.
also critical for color vision. C for C cones. Cones are extremely abundant in the foveal region. Fovea. Next, bipolar cells. They are a simple cell that is going to receive signals from rods and cones and send the information to ganglion cells. Ganglion cells is the most important out of all. Why, sir? These ganglion cells are the only output cell of retina.
road for
They are
night.
going to go out of retina in the form of optic nerve, that is our cranial nerve 2. The axons of ganglion cells forms our optic nerve, and they are also the only cell capable of generating action potential. All the credit goes to ganglion cells, producing action potential ganglion cells. These horizontal cells and amacrine cells are connecting cells. I told you they sharpen our visual signal by lateral inhibition. If they ask you lateral inhibition, which cells are involved? Horizontal cells, amacrine cells. These amacrine cells are considered to be the purely depolarizing cell. What is depolarization? What is hyperpolarization? In the next slide you will understand. For the time being, remember, there is only one cell that is purely depolarizing. There is no hyperpolarization. The pure depolarizing cell is amacrine cells. And finally, I told you Muller cells, no role in vision. They are a simple supporting glial cells. That is why we call them as retinal glial cells.
Retinal
Or
glands,
GC,
yes.
Muller cells. So 7 cells. 6 have a role in vision, except only one. That one, no role in vision, Muller cells. Now, I am surrounded by a bright light here in this room. By any chance, if we switch off this light, the entire room will go into dark mode. So our eye will experience only 2 states. Either the light state or switch off the light, it goes into dark state. What will happen, sir? We will take the example of rods. If we switch off the light, that means in dark state, our rods, there is a cyclic GMP dependent sodium channel, which is in none other but what group of channels are they?
Funny
Remember,
currents.
they are our funny currents.
Yes.
These funny current channels remain open in the dark. Open in the dark, sodium channel. So who will come inside? Sodium will come inside. If sodium is coming inside, what we call that state as depolarization. Or depolarization, leading to release of neurotransmitter, that is glutamate. So dark will have a neurotransmitter release, glutamate. In dark, funny current channels are open. They are opened with the help of cyclic GMP. Sodium comes inside. Dark means depolarization. Dark means glutamate release.
Dark.
Let us all switch on this light. If we switch on, light will strike our eye. It will strike our retina. What the light is going to do? Light does only one thing. It converts Leven's retinal to all trans retinal. So this all trans retinal you see only in the light state. This all trans retinal is going to activate something called as transducing in the light state. This transducing further activates something called as a phosphodiesterase What is this phosphodiesterase? Biochemistry. Phosphodiesterase is the degrading enzyme. It degrades our cyclic GMP. Remember, all these are going to happen in the light state. So with the help of phosphodiesterase, we are degrading cyclic GMP. When there is no cyclic GMP in the light state, these sodium channels will not remain open. To open the sodium channels, you need cyclic GMP. In light state, there is no cyclic GMP. They are destroyed by your phosphodiesterase. So no cyclic GMP. The
No
sodium
cyclic
channels
GMP,
will not
no
open.
sodium
There is no
influx.
depolarization. On the other hand, this potassium movement still keeps on going outside. This movement of potassium leads to
Hyperpolarization.
hyperpolarization. So when will you get in hyperpolarization?
Light
state.
stage.
Dark state means depolarization.
Depolarization.
Light state means hyperpolarization. Our sodium channels are closed in light state. So there is no depolarization. What will you get is hyperpolarization. You get neurotransmitter release in dark state. The neurotransmitter release is decreased in the light state. That's all. So this light forms altrans-retinal, which activates transducing, which activates phosphodiesterase, cyclic GMP degraded, sodium channels closed, no depolarization, hyperpolarization in light state. Very important MCQ asked many times before. Hyperpolarization, light state. Next, the sodium channels close in which state? Light state. Eventually leading to hyperpolarization. Now guys, from retina, the information goes to thalamus, where the thalamus are lateral geniculate body, LGB, simple. Our lateral geniculate bodies have 6 well-defined layers. First one, out of this, the layers 1 and 2, they have large cells, obviously become magnocellular layer. The remaining layers 3, 4, 5 and 6, they have small cells. Small means parvo. So magnocellular means 1 and 2. Parvocellular means 3, 4, 5 and 6. So correspondingly, we are going to have two major pathways. What are they? Magnocellular pathway, parvocellular pathway. Magno means layer 1 and 2. Parvo means layer 3, 4, 5 and 6. Where they will go from thalamus, they will go to visual cortex. Which layer? Layer 4 of visual cortex. Which layer? Layer 4 of visual cortex. Why you need two pathways? M, magnocellular, is for eye
M for
movement. Very, very important concept. Underline M, underline M. Magnocellular for regulation of eyeball movements. Parvocellular is very, very important for color vision. Not only that, all the finer details. Very important. So magnocellular for eyeball movement regulation. Parvocellular for color vision and finer details. There is one minor pathway that originates from K cells. What we call that pathway, sir, remember, coniocellular pathway. It's separate one. Third one, very minor one, playing a role in detection of blue color or color vision. They may ask you this question. Coniocellular pathway, minor third pathway, originates from the K cells. This coniocellular pathway is important for detecting blue color vision. That's all. Magnocellular for eyeball movements, parvocellular for color vision and finer details, coniocellular pathway for blue color. Now, let's look into this right lateral geniculate body. Even though it is present in the right side, it is going to receive information from both the eyes. Right lateral geniculate body receive information from both the eyes. That means what? Layers 2, 3, 5 receive information from the same sided eye. That means what? Right LGB, right eye. Coming to which all layers? 2, 3, 5. What about the remaining layers? 1, 4, 6. Contralateral eye. That means what is the eye here? Left eye. That's all. Same sided LGB receive information from the same sided eye in layers 2, 3 and 5. The remaining layers 1, 4, 6 receive information from the opposite eye, that is left eye. So right lateral geniculate body receive information from both the eyes. 2, 3, 5, same side. 1, 4, 6, remaining opposite side. Simple. So from thalamus LGB, the information goes to cortex. That's the most important 17, 18, 19, which is our visual cortex, which is also called by this special name striate cortex or remember guys, striate of Genari. Very important MCQ. Striate cortex or striate of Genari, area 17, 18, 19, where it is located in the calcrine sulcus.
ऑक्सीपिटल लोब पीछे के भाग में 17, 18, 19 visual cortex, thalamus, visual cortex, stria of January, area 17, 18, 19, and it is in calcarean sulcus of occipital lobe. It is of occipital.
Of which lobe? Occipital lobe. Striate cortex or stray of January, most importantly Brodmann area 17, 18, 19, visual cortex. This visual cortex, out of all the functions, extremely critical function is detecting this. Able to find out what is this Ishihara chart, remember?
Yes.
But we test using this color vision. This color vision has got a separate pathway. It sorts from the retina with the help of cones. What are those special cones? I will tell you. From retina, the information goes to thalamus, which important pathway I told you. Most importantly, parvocellular pathway, thalamus. Finally goes to cortex, to this important group of cells for color vision, blobs. Now our focus is primarily on these retinal cones. They are three important types. Now look very carefully. What are those three types? What are those three primary colors? Red, green, blue. Yes. There are three cones. Red is having long wavelength. That is why L cone. Blue is having short wavelength. That is why S cone. The one in between, medium wavelength. That is why M.
RGB lights, guys.
So L cone detect red.
Natural RGB
medium
lights
cone detect
detector
green,
in our eyes.
short wavelength detecting cone detect blue. By any chance, if this L cone is deficient, you will not be able to see red color. What we call that defect as protanopia. Very important.
Deuteranopia.
If this M cone is deficient, you will not see green color. What we call that as deuteranopia. And finally, if the S cone is deficient, you will not see blue color. What we call that as tritanopia. That's all. Not detecting red color, protanopia. Not detecting green color, deuteranopia. Not detecting blue color, tritanopia. This is about color vision, cones, and the important abnormality. Right, guys. In special senses, from vision, let's move on to the next important one, that is hearing. The receptors for hearing is located in cochlea. Very simple understanding. Our cochlea is divided into three parts by two membranes. What are those two membranes, sir? The first one, very important one, on top, what we have is Reisner's membrane. On the base, look carefully, on the base, what we have is the basilar membrane. So cochlea will be divided into three parts by two membranes. On top we have Reisner's membrane, on the base we have basilar membrane. Now what are those three parts, sir? Very simple, guys. The one that is in the middle is always media. Middle is media, scala media. The one that is on the top, we call this as scala vestibuli, and the one that is below, we call this as scala tympani. I told you very simply. Two membranes, Reisner membrane and basilar membrane, split our cochlea into three parts. Middle part is media. On top we have scala vestibuli, below we have scala tympani. So very, very important. Where the receptors are located in this particular region. What is this important arrow pointing towards? Organ of cortex, where the receptors for hearing are located. What are those, sir? They are none other but our hearing receptor. Particularly this organ of cortex, this hair cells are surrounded by a special membrane. You are able to see here. What is this membrane called as, sir? This membrane is called as tectorial membrane. So the receptors for hearing, organ of cortex, surrounded by a membrane, tectorial membrane. So the nerve fibers that innervate these hair cells converge onto a ganglia. What is that ganglion called as, sir? Spiral ganglia. This is our spiral ganglia. They eventually combine together to form which important cranial nerve, sir? 8th cranial nerve. Particularly the part we are interested here is the cochlear division. That's all. So the nerve fibers come to spiral ganglia, which eventually converge together to form the 8th nerve, cochlear division. So two membranes divide our cochlea into three parts: scala media, scala vestibuli, and scala tympani. It is actually in the middle region, the media part, the receptor hair cells are present in the organ of cortex in scala media. Now let's magnify and see our organ of cortex. Two important hair cells, outer hair cells and inner hair cells. We call them as OHC, IHC. I told you, the hair cells are specially covered by tectorial membrane. Very, very important concept. This hair cells, inner hair cells and outer hair cells are actually the receptors. The most important first point, outer hair cells, inner hair cells, receptors for hearing. The tallest cilia, that is found in the hair cells is called as kinocilium, the tallest cilia. Okay. You further have many smallest cilia. There are many in them. We call them as stereo. Okay, very important. The tallest cilia in the hair cell is called as kinocilium. The smallest cilia found in our hair cells are called the stereocilia. If all the hair cells bend towards the tallest one, remember the tallest one is our kinocilium. If all bend towards this kinocilium, it leads to depolarization, which is exclusively because of influx of potassium ions here. Very, very unique finding. The only location in human body, depolarization due to potassium influx. In all locations it is sodium influx, but here it's an exception. Depolarization due to potassium influx, hair cells. If all the hair cells bend towards the kinocilium, leading to depolarization. That is how they process signal and send the information.
નોર્મલી ડિપોલરાઇઝેશન કેનાથી થાય? સોડિયમ ઇન્ફ્લક્સ થાય, પણ અહીંયા ડિપોલરાઇઝેશન થશે પોટેશિયમ ઇન્ફ્લક્સ થી. આ યાદ રાખવા જેવી વસ્તુ છે. This is to be remembered, guys. Yes, yes. Beautiful star. Nice. All hair cell bends towards the kinocilium. All hair cell bends towards the kinocilium, which is the longest, and depolarization happens due to influx of the potassium. Potassium is inside, and this method is autoacoustic emissions.
We have seen a very important membrane, guys. Basilar membrane, ENT and physiology, recent MCQ. It has got base. We are clearly seeing that is broader. This base part is very, very, very close to oval window. Remember, guys, the sound waves having high frequency, remember, high frequency causes vibration that is best in the base part. So basilar membrane,
High
base part is
frequency
broader,
base,
very
low
close to oval
frequency
window. The sound waves having
apex.
high frequency causes vibration best in the base region. On the other hand, apex we are clearly seeing it is
Base,
narrower.
broad,
The
oval,
apex is
high
close to
frequency. Apex, narrow,
helicotrema.
helicotrema.
Yes, next important point. It is the
Low
low
frequency.
frequency sounds causing vibration best in the apex part. So base is broader, high frequency waves causes vibration best here in the base. Apex is narrower, low frequency sounds causes vibration best in the apex. Low frequency apex, high frequency peaks the vibration. Now, we have a very special dedicated pathway for hearing. We easily remember this with the help of mnemonic E colon MA symbol. What is E, sir? Our eighth nerve cochlear division, which goes to cochlear nuclei. What does O stands for? It is the sun. Superior olivary nucleus, where most importantly, remember this aspect, direction of sound. If you're walking in the road, if someone is clapping, you can immediately turn towards that side. The direction processing starts in superior olivary nucleus. Then the information goes to lateral lemniscus. Then goes to inferior colliculus. This is one more area very, very, very critical for direction processing. So direction processing superior olivary nucleus, inferior colliculus. Then goes to our thalamus. What important nucleus in thalamus are medial geniculate body. Vision, lateral geniculate body. Hearing, medial geniculate body. Finally goes to auditory cortex. Look carefully. The auditory cortex is located in the temporal lobe. Where exactly? In the superior temporal gyrus. It is also called as Hessel's gyrus. So finally culminating in the auditory cortex, the superior temporal gyrus in the temporal lobe, that is our auditory cortex, also called as Hessel's gyrus. This auditory pathway, E colon MA, even they ask to arrange the sequence of passage of information in one INC. Remember this mnemonic E colon MA, auditory cortex.
8. Now, cochlea. Superior colliculus, नहीं, superior olivary nucleus, lateral lemniscus, then inferior colliculus. Superior olivary nucleus, lateral lemniscus, inferior colliculus, then inferior colliculus, lateral, then medial geniculate body, vision lateral geniculate body, medial geniculate body, and then auditory cortex, which is in the superior temporal region. 8th nerve, then cochlea, then superior olivary nucleus, then lateral geniculate, नहीं, lateral lemniscus, inferior colliculus, geniculate body गई, medial geniculate body, and auditory cortex in the superior temporal region. Gyrus of temporal lobe.
Fixing the superior temporal gyrus. Now, from hearing, let's move on to a fascinating sense of smell. Remember olfaction. Any good smell that is any good smell surrounding us, we get to take a deep breath. Wow, we say, why we take a deep breath? Because the olfactory receptors are present very high up in the nose. Where, sir? In olfactory epithelium. And the receptors are actually bipolar neurons, which combine together to form the cranial nerve 1, olfactory nerve. The receptors are the bipolar neurons, very important, bipolar neurons. In the olfactory epithelium, other than receptors, you also see certain supporting cells called sustentacular cells. High regenerating capacity, olfactory epithelium, because they have lot of stem cells, basal stem cells. So receptors are there. Supporting cells, first tentacular cells are there, and basal stem cells are there. So from this olfactory epithelium, the information goes to the bulb region. What is this bulb? Is an olfactory bulb, where you see 4 important type of cells: mitral cells, tufted cells, periglomerular cells, granule cells. Mitral cells and the tufted cells are excitatory. They use the neurotransmitter glutamate. Periglomerular cells and the granule cells are considered to be inhibitory. They stop the information there itself because they use GABA as neurotransmitter. Simple. Mitral, tufted, excitatory, use glutamate. Periglomerular, granule, inhibitory, they use GABA as neurotransmitter. So from olfactory bulb, the information will be projected to certain higher centers.
Bipolar location of the part of the nose, olfactory contains bipolar neurons, tentacular cell, supporting basal stem cell which are regenerated. હું વેન્ટ્રો વીપીએલ હતું ને, વેન્ટ્રોપોસ્ટ્રોલેટરલ હતું, વેન્ટ્રોપોસ્ટ્રોલેટરલ સેન્સરી હેમિસ્કસ હોમોન્ક્યુલસ, સેન્સરી હોમોન્ક્યુલસ એન્ડ હવે છે લેટરલ જેનિક્યુલેટ બોડી વિઝનમાં છે, અને લેટરલ જેનિક્યુલેટ બોડી થેલેમસ છે, મીડિયલ જેનિક્યુલેટ બોડી છે એ હિયરિંગમાં છે, ડોર્સોમીડિયલ થેલેમસ છે એ ઓલ્ફેક્શનમાં. સો olfactory bulb, role of the central areas, receives information from olfactory bulb, ventral postrolate medial, VPL, lateral હતું તો એ VPL હતું એ સેન્સરી છે, પણ વેન્ટ્રલ પોસ્ટ્રો મીડિયલ છે એ ટેસ્ટ માટે છે. VPM is for test, VPL is for sensory, and lateral genicular, medial genicular થઈ ગયું, અને dorsomedial is for the olfaction. Okay. Mitral cell and tufted cell, inhibitory cells, અને glutamate. આ બે સેલની અંદર ગ્લુટામેટ હોય, આમાં ગાબા યુનિવર્સલ ઇનહિબિટરી ન્યુરોટ્રાન્સમીટર ઓલવર્સ.
Which is considered to be the olfactory cortex or orbitofrontal cortex. Humans can consciously discriminate. Remember, discrimination of order. We can definitely say what order is this. This conscious discrimination of order is possible with the help of our olfactory cortex or orbitofrontal cortex. Then, certain smell evokes certain emotions. So, smell and emotion processing are amygdala. Remember, certain smell evoke beautiful memories. If this perfume smell is somewhere here, we can clearly say this person is somewhere around. Which important area? Entoanal cortex. So conscious discrimination, differentiation of orders, got.
Olfactory cortex and orbitofrontal cortex. Conscious discrimination of means this is the sweet smell and this is the sour smell. That amygdala processing of emotion evoked by smell. What a smell! What a smell! And entorhinal cortex is like processing of memories evoked by. Oh, what are that days? What are those days? Nice days.
Olfactory cortex, orbitofrontal cortex. Smell and emotions, amygdala. Smell and memories, entorhinal cortex. This is about smell.
Emotions, memories, entorhinal memory, amygdala emotion.
5 basic taste sense are there for humans. The one we tremendously love, sweet, sour, bitter, salt, umami. Umami is the recent one. Remember, guys, the recently added 5th taste because of monosodium glutamate. Those taste senses, their receptors, very high in topic. They will definitely ask you, very high in the table, guys. How to remember this? Salt, sodium is an ion. Sour, H plus is an ion. That means they use ionotropic receptors.
H plus.
Salt, sodium ion, sour, H plus ion, acid, ionotropic receptor. The remaining 3, sweet, bitter, umami. G protein coupled metabotropic receptors. That's all. Now the names. TR stands for taste receptor. For sweet sensation, the isoforms are important. T1 R2, T1 R3. Sodium, salt, epithelial sodium channel.
This is important. See. Salt અને સોર વાળું તો બરોબર છે. એપિથેલિયલ સોડિયમ ચેનલ ઇનેક, આમાં ઇનેકની સાથે સાથે HCN ટીઆરપી ચેનલ છે. ટીઆરપી ચેનલ છે સોરમાં. હવે T1 R2 and T1 R3 is for sweet. ઉમામી માટે 1 and 3. અને બીટર માટે 2R 2R for bitter. ઉમામી માટે 1 and 3 અને સ્વીટ માટે ઉમામી માટે 1 and 3, સ્વીટ માટે 2 and 3. T1 R2 T1 R1 umami, T1 R3 umami, T1 R2 sweet, T1 R3 sweet, T2 R is bitter. Maglu R for alag જ, so it's umami. TRP channels is for sour taste. E negative channels is for sour taste. Only E negative for salty taste, obviously.
So H plus ions, HCN channels, ENAC channel, and a special type of DRP channel. This was the recent NEET MCQ. Sour toast is mediated by a special group of DRP channels, inotropic receptor, sour taste DRP channels. Bitter T2R receptor, umami glutamate, mGlu-R4. This is most important. Remember this for umami. Metabotrophic glutamate receptor. Also additionally for umami, remember T1R1, T1R3. So what were the expected MCQs? Epithelial sodium channels for salt, DRP channels for sour, metabotrophic glutamate receptor for umami. This table is very, very important. Now, how the taste sensation is conveyed? Very simple, guys. From the tongue, anterior 2/3, posterior 1/3, and posterior most palate pharynx. Which cranial nerve is very simple. Anterior 2/3 by the caudate tympanic branch of facial nerve, posterior 1/3 by our glossopharyngeal nerve, palate regions through vagus nerve. They go to medulla, where you have the taste integrating center, that is nucleus tractus solitarius. From medulla, it will be projected to thalamus, which important nucleus ventro-post-medial nucleus eventually goes to the higher order center, that is our taste cortex. Where is taste cortex? It is present in the anterior insula and this area, frontal lobar field. They are considered to be taste cortex in humans.
Ventral post-medial VPM. VPL is for sensory cortex.
This is about taste sensation. Alright guys, let's shift our attention from sensory physiology to motor physiology.
Okay. Let's take a break or not? Chat, only one person is there. Take a break or not? If you are not typing anything, then I cannot. It's been 42 minutes. Okay, let's not take a break. Let's just finish this.
First and the foremost important point, sensory physiology is ascending. Sensory aspects are ascending. On the other hand, motor pathways are classically descending. That means top to bottom. In brain, particularly in the cortex.
Generally, sensory physiology is ascending physiology. Sensory physiology is ascending physiology. Sensory physiology is ascending because it senses. Then comes motor, which is descending. Okay.
Next, we will see second motor areas. The information goes down, descend to spinal cord, where you will see alpha motor neuron and the gamma motor neuron for motor control. From this spinal cord, the information goes down to control of skeletal muscle. So brain cortex, spinal cord, motor neurons, finally to the skeletal muscle. So first, brain cortex. What are these motor areas? Three important areas are there. Look very carefully in the picture. The most important one, primary motor cortex, PMC. Then we have premotor cortex and supplementary motor cortex. What are these area numbers? What function do they provide? Let's look at the classical example for a writing. Primary motor cortex, what is its role? See, sensory cortex is post-central. Motor cortex is pre-central. Motor cortex is frontal. Which Brodmann area? 4. I'm going to write down this execution of the final motor movement. Writing the execution part is done by primary motor cortex. Then what is the role of remaining two? We have premotor, which is obviously Brodmann area 6. 4 is primary motor. Brodmann area 6, that is anterior to the precentral gyrus, premotor cortex. See, I told you writing. So during writing, I assume a particular body posture. The orientation of the body for movement, okay, I'm writing like this. So this orienting the body for movement is premotor cortex. Supplementary motor cortex, it is also Brodmann area 6. Suppose, for example, a motor active driving. Driving means you need the help of two-hand control. This bi-manual coordination while performing any complex task, supplementary motor cortex. So execution, primary motor cortex. Orienting the body, premotor cortex. Bi-manual coordination for complex tasks, supplementary motor cortex. Now, there are certain important tract pathways. Motor physiology means obviously pyramidal tract, corticospinal tract. Let me introduce you to that. We have corticospinal tract and corticobulbar tracts, which are our pyramidal. Other than these two, any other motor control pathway is extrapyramidal. What are the extrapyramidal tract? 4 in number. We have tectospinal, rubrospinal, vestibulospinal, reticulospinal. Yeah.
Okay. Pyramidal tract, corticospinal, corticobulbar. Then extrapyramidal tract. These are pyramidal tracts. These are extrapyramidal tract. Extrapyramidal tract are tectospinal, rubrospinal, vestibulospinal, and reticulospinal. So બધા સ્પાઇનલમાં જાય છે. તો ટેક્ટમથી સ્પાઇનલમાં, રૂબ્રો રેડ ન્યુક્લિયસથી સ્પાઇનલમાં, વેસ્ટિબ્યુલર કોર્ટેક્સથી સ્પાઇનલમાં અને રેટિક્યુલર નેટવર્કથી સ્પાઇનલમાં. સો TRVR, ટેક્ટો રૂબ્રો વેસ્ટિબ્યુલો રેટિક્યુલો, ટેક્ટો રૂબ્રો વેસ્ટિબ્યુલો રેટિક્યુલો. સો કોર્ટિકોસ્પાઇનલ કોર્ટિકોબુલ્બર હોય અને ટેક્ટો રૂબ્રો વેસ્ટિબ્યુલો રેટિક્યુલો હોય. ઓકે. સો લોકેશન કેવી રીતે છે? તો કે એક્સ્ટ્રા પિરામિડલ ટ્રેક અહીંયા છે અને પિરામિડલ ટ્રેક અહીંયા. તો કોર્ટિકોસ્પાઇનલ ટ્રેક અહીંયા આવી ગયો. રૂબ્રો સ્પાઇનલ ટ્રેક એની અહીં રહે છે. ટેક્ટો રેટિક્યુલો વેસ્ટિબ્યુલો અહીંયા. બરાબર. વેન્ટ્રલ ડોર્સલ. સો dorsal. On the ventral side, we have VRT, reticulovestibulo-tecto, tecto-reticulovestibulo. T वाला vestibulo, reticulo, tecto, T वाला. અને રૂબ્રો તો અલગ જ થઈ ગયો, રૂબ્રો સ્પાઇનલ. સો ટી वाले पाथवे सारे एक तरफ, रूब्रो स्पाइनल एक तरफ with the corticospinal. Okay.
Other than our pyramidal tract, so obviously they become the extrapyramidal tract systems. Now look into this beautiful diagram. A classical observation you have to make, my dear friends. Let me put a box first and foremost. For vestibulospinal, for reticulospinal, for tectospinal, these three are classically same in the medial side. That is why they are classically called as
Medial motor pathway.
They descend medially. What are all those three medial motor pathways? Vestibulospinal, reticulospinal, tectospinal. On the other hand, look very, very carefully, my dear friends. Ending in the lateral side. Lateral motor pathways. What are these lateral motor pathways? Our lateral corticospinal tract and the rubrospinal tract. Even though this rubrospinal tract is considered to be an extrapyramidal tract, but it is an exception in the sense that this extrapyramidal rubrospinal tract descends laterally. All the other remaining extrapyramidal tract descend medial. So we have medial motor and lateral motor pathway. What is the significance? First, let's try our lateral corticospinal tract and rubrospinal tract. Lateral corticospinal, rubrospinal. They are for controlling fine motor movement, skilled motor movement, voluntary motor movement. The classical example, remember, writing. Writing is a fine movement. Writing is a skilled
Lateral
movement.
motor pathways, corticospinal tract, rubro. Let me.
Lateral corticospinal tract and the rubrospinal tract. Even though this rubrospinal tract is considered
मेंशन करो ना कोई जो डोर्सल करो एंटीरियर ना करो ना एंटीरियर corticospinal tract.
to be an extrapyramidal tract, but it is an exception in the sense that this extrapyramidal rubrospinal tract descends lateral. All the other remaining extrapyramidal tract descend medial. So we have medial motor and lateral motor pathway. What is the significance? First, let's try our lateral corticospinal tract and rubrospinal tract. Lateral corticospinal, rubrospinal. They are for controlling fine motor movement, skilled motor movement, voluntary motor movement.
Fine,
Classical
skilled,
example,
voluntary.
remember, writing. Writing is a fine movement, writing is a skilled movement, writing is a voluntary movement. Which group of muscles are involved here? Remember, they are predominantly involved in control of flexors, finger flexors. Yes. Lateral motor pathway is for fine, skilled, voluntary movement control. The classical example is writing. Lateral motor pathways control our flexors. Medial motor pathway, what are the ones? Vestibulospinal tract, ectospinal tract and our reticulospinal tract. Extremely important for control of posture. Posture means we definitely have to regulate our extensors. What are these extensors? We classically say, remember, they are our anti-gravity muscles. So medial motor pathway is for controlling posture. We predominantly going to control extensors, medial motor path, which are our anti-gravity muscles. Now, when this pathway are lesion, the affected individual assumes certain postures. Two important postures. The first one is decerebrate rigidity. But all observations here, guys, look very carefully and see. The lower extremities are extended. Yes, sir, true. The toes are pointing inward. Yes, sir, true. The upper extremity is also extended. Upper extremity is also extended. The fingers and forearms are pronated. Yes. Finally, the neck we are clearly seeing extended. That means there is uniform extension. We also call this as extensor rigidity. Which one? Decerebrate rigidity. There is uniform extension. So there is leg, arm extension, neck extension. Everywhere there is extension, extensor rigidity, which is decerebrate. Now to contrast this with decorticate. Decorticate. What all the classical observation? See, the lower extremities are extended, yes. So the toes are pointing inward, similar, yes. But the upper extremities, this is where the difference. The upper extremities are flexed. So what is the reason for this flexion, sir? They will ask you this MCQ. Being unique, they will ask you. Because of the intactness of rubrospinal tract. This rubrospinal tract, what I told you, they control flexors. So the difference, the upper extremities are flexed because of rubrospinal tract that is intact here in the cortical responsible for the flexion only in the upper extremities. The head you also see here is extended. So everything is similar except the upper extremity flexion in the cortical rigidity because of intactness of rubrospinal tract that is going to control our flexors. Next important thing. They will ask you the differences between upper motor neuron lesion, that is UMN lesion, and lower motor neuron lesion. See, it is the lower motor neuron that directly goes to muscle. So the muscle findings like muscle atrophy, muscle fasciculations, you classically see in lower motor neuron lesion. You will not see them in upper motor neuron lesion. See, lower motor neurons, alpha and gamma, they go directly to skeletal muscle. So their lesions affect the muscle as such. So muscle atrophy, muscle fasciculations, you see them in the lower motor neuron lesion. Tone is increased, hypertonia in upper motor neuron lesion. Tone will be decreased in lower motor neuron lesion. Remember, the weakness is regional. Region-based weakness, see, upper limb weakness, region-based weakness. On the other hand, lower motor spinal cord means it is segments. You classically see segmental type of weakness in lower motor. See, upper motor, extremities are extended.
Decerebrate, extended, corticate, oh, left, cerebrate, extended, cerebrate, extended.
Next important thing, they will ask you the differences between upper motor neuron lesion, that is UMN lesion, and lower motor neuron lesion. See, it is the lower motor neuron that directly goes to muscle. So the muscle findings like muscle atrophy, muscle fasciculations, you classically see in lower motor neuron lesion. So you see them in the lower motor neuron lesion. Tone is increased, hypertonia in upper motor neuron lesion. Tone will be decreased in lower motor neuron lesion. Remember, the weakness is regional. Region-based weakness, see, upper limb weakness, region-based weakness. On the other hand, lower motor spinal cord means it is segments. You classically see segmental type of weakness in lower motor. See, upper motor, regional weakness, lower motor neuron, segmental weakness. Reflexes are exaggerated, we call as hyperreflexive, upper motor neuron lesion. The reflexes are sluggish or reduced in lower motor neuron lesion. And finally, the classical differentiating point, what is that? Babinski's sign is positive in upper motor neuron lesion. So Babinski's sign positivity you see in upper motor neuron lesion. This is about human and element, their salient differences. Alright guys, the next important area in motor physiology is about the understanding of reflexes. Let's start with the simplest possible reflex, stretch reflex. Stretch reflex means invariably you have to remember muscle spindles, that's all. The receptor for stretch reflex is muscle spindle. First look very carefully. Whenever you stretch any muscle, the muscle spindles will be activated. This muscle spindle send the information through a sensory nerve. In response to that, the sensory nerve is the efferent. Our spinal cord will send the efferent. What is this efferent motor nerve, sir? Alpha motor neuron. Where it goes, look very carefully where it goes. It is going to activate our actin and myosin. And cause their interaction, eventually leading to muscle contraction. So stretch. Muscle spindles are activated. Efferent information goes to spinal cord. In response to that, the spinal cord gives the efferent, that is alpha motor neuron, coming back to the muscle, activating actin myosin, leading to muscle contraction. So it is this stretch that induces muscle contraction through the help of this receptor muscle spindles. How the muscle spindle looks like? Look very carefully. Very important type. This muscle spindle, nucleus arranged inside a bag-like structure, it will become nuclear bag fibers in muscle spindle. If the nucleus is arranged in the form of a chain, we call them as nuclear chain fibers, broadly speaking. Nuclear bag fibers in muscle spindles, nuclear chain fibers in muscle spindles. There are two important types of bag fiber. We call them as dynamic nuclear bag fiber, static. Remember, static nuclear bag fiber. There are two types of nuclear bag fibers: dynamic nuclear bag fiber, static nuclear bag fiber. So overall, you will have dynamic bag fibers, static bag fibers, chain fibers. That's all. This muscle spindle.
Nuclear bag fiber, we have two types: nuclear, dynamic nuclear and static nuclear. Nuclear chain fiber are static. Okay. The sensory nerve, bay ending, primary ending, secondary ending, annulospiral ending, lower spray ending, lower spray, spiral ending, then nuclear bag fiber, static nuclear bag fiber, all three. 2 goes to 2, only static, static nuclear chain fiber, static. So static only this, and all three 1. Okay, we are done.
We receive sensory information. What are those sensory nerves, sir? We have group 1A and group 2. This group 1A primary is also called as annulospiral endings. This group 2 is also called as flower spray endings. Remember, it is the sensory efferents. Muscle spindle. Group 1A means primary annulospiral. Group 2 means secondary flower spray. Now the most important MCQ. Primary annulospiral goes to all three. That means it goes to dynamic bag fibers, static bag fibers, and chain fibers. But the secondary goes only to 2. But all those 2 secondary flower spray going only to 2 important areas: static nuclear bag and nuclear chain fiber. That means no dynamic, very important, bag fibers. So secondary ending is not to dynamic bag fiber. Secondary ending goes only to static bag fibers and chain fibers. But primary goes to all. That's all. Now, the reflex pathway, stretch reflex, which we commonly do in clinics. What is the stimulus, doctors? You need stretch. That's all. In response to this, our receptor muscle spindles are activated. So automatically it is going to send the information to spinal cord. Spinal cord is actually considered to be the center. Very, very important. Now, how the information goes to spinal cord? With the help of efferents. What are those efferents? Group 1A and 2. 1A is primary annulospiral, 2 is secondary flower spray. So through this efferents, the information goes to spinal cord. In response to that, the spinal cord gives efferent. I told you, very simply, it is the alpha motor neuron. The alpha motor neuron further is sent down to the effector, which is our skeletal muscle, where it will go in the effector, actin and myosin. And their interaction eventually leads to muscle contraction. Close your eyes and imagine. Stretch, muscle spindle, sensory efferents 1A and 2, going to center spinal cord. In the spinal cord, efferent alpha motor neuron, coming down to skeletal muscle, actin and myosin, their interaction, muscle contraction. That's all. Now, this is about alpha motor neuron that goes to skeletal muscle, actin and myosin. Now, this is the point of confusion for many. What is this, sir? This muscle spindle itself is having a motor supply. See, overall muscle, actin and myosin innervated by alpha motor neuron, that is separate. This muscle spindle, the receptor by itself is having a separate motor supply. To understand that, very simple. Look very carefully. This is the center part, which contains the receptor, the muscle spindle proper. It also has got 2 peripheral endings. It is in this peripheral endings. The innervation is gamma motor neuron. The innervation is gamma motor neuron. So in muscle spindle center, you see the receptor. The peripheral ends are the one receiving innervation from gamma motor neuron. Important points, what I told you so far. Muscle spindles, gamma motor neurons. Back, not to the center, to the peripheral contractile part of muscle spindle, gamma motor neuron. Activity of this gamma motor neuron increases the sensitivity of stretch reflex. You can get very good muscle contraction. So there are 2 important modes of muscle contraction. You activate alpha motor neuron, muscle will contract. You activate gamma motor neuron, then also muscle will contract. So
activate alpha, muscle contracts. Activates gamma, muscle contracts. Activate both, muscle spindle.
muscle can be contracted either by alpha motor neuron or gamma motor neuron. That is why for all useful contraction, body uses both alpha and gamma activated together at the same time. We call this as alpha gamma co-activation.
Golgi
So alpha motor neuron can
tendons.
cause contraction. Gamma motor neuron through muscle spindles can also cause contraction. Human body utilizes both of them at the same time. Alpha gamma co-activation. See, now this is about stretch reflex. Stretch induced contraction. On the other hand, during experiment, enthusiastic person, if he is trying to overstretch, that muscle will not contract for you. Any overstretched muscle always undergoes relaxation. This is to prevent muscle injury. Stretch, contraction. Overstretch, muscle can be injured. Relaxation. What is this reflex, sir? Overstretch, relaxation, inverse stretch reflex. Opposite of stretch. Inverse stretch reflex. What is the receptor here for this, sir? Remember, very important, Golgi tendon organ symbol. So for stretch reflex, it is muscle spindle. Inverse stretch reflex, it is the Golgi tendon. If you want to understand both these two reflexes, a very important table, this will make everything clear. Stretch reflex means muscle spindle. Inverse stretch reflex means Golgi tendon. Stretch reflex is very important for detecting muscle length. Inverse stretch is going to detect the muscle tension. So spindle is length sensing. Tendon organs are tension sensing. Important. The efferent. For stretch I told you group 1A and 2. For Golgi tendon organ it is 1B. The center is spinal cord for both. Look very carefully. The efferent is alpha motor neuron. Is alpha motor neuron for both the reflexes. But in one reflex we actually see contraction. In other reflex you actually see relaxation. How? Because in one reflex alpha motor neurons are activated. In the other reflex, alpha motor neurons are inhibited. Stretch reflex, alpha motor neuron activation, contraction. Inverse stretch reflex, alpha motor neuron inhibition, relaxation. For stretch, one synapse, monosynaptic. For inverse stretch reflex, two synapses, disynaptic reflex. The other name for a stretch reflex is, remember guys, very important, myotatic reflex. The other name for inverse stretch reflex, remember it is also called as lengthening reaction. Remember this facts. Stretch reflex is also called myotatic reflex. Inverse stretch reflex is also called lengthening reaction. Overstretch, lengthening the reaction. Lengthening reaction is inverse stretch reflex. Final take home message. Two reflexes, spindle. LE is highlighted. That means it is length sensing. In Golgi tendon organs, 10 is highlighted. That means it is going to be tension sensing. Very important. So the length sensing ones are spindles. The tension sensing ones are tendon organs. Right? Stretch reflex, inverse stretch reflex. See, we all go to beach while walking. Any sharp object piercing your this individual, this is right side, this is left side. Right foot, there is a small pinprick. What will happen? We are clearly seeing the right limb is undergoing flexion. The left limb is undergoing extension. This is a classical example for a polysynaptic reflex. Which reflex? Withdrawal reflex. What is actually happening? The response in the right limb. Flexor muscles are activated. Extensor muscles are inhibited. Remember, here flexors are activated, extensors are inhibited. There is flexion. This is neither. Withdraw the limb away from the painful stimulus. Just take the limb away, and this will withdraw the reflex. What is happening in the opposite side here? Extensors are activated, flexors are inhibited.